4:51 p.m. December 15th, 1967. Christmas shoppers jam the Silver Bridge over the Ohio River. Then, without warning, without sound, the entire 1750-foot span drops into the freezing water below. 46 vehicles, 64 people on the deck. In under 2 minutes, the entire structure, steel, concrete, cars, lives, plunges into the icy Ohio. 46 dead. The bridge simply ceased to exist. How does a bridge, engineered, inspected, trusted for 40 years, vanish in seconds? The answer lies in a single piece of steel, 2 inches wide and a crack no inspector ever saw. The Silver Bridge wasn't held up by cables, it was held up by chains. Massive steel eyebars, each one forged with a circular eye at both ends, linked together like a colossal bicycle chain stretching 1,750 feet across the Ohio River. Each eyebar slid through the eye of the next, held by a single steel pin. Elegant, yes, but here's the catch. If any one eyebar failed, the entire chain would separate. No backup cables, no redundancy. Every link was a single point of failure. And that's exactly why the Silver Bridge was different from every modern suspension bridge you've ever seen. Those use woven wire cables with thousands of strands. Lose one strand, the bridge stands. Lose one eyebar, the clock starts ticking. But the real killer wasn't visible to anyone walking across that bridge. Deep inside eyebar 330, a single steel link in the suspension chain, a microscopic crack, had been growing silently for years, atom by atom. Every car that crossed, every truck, every bus, bent that eyebar just slightly. Thousands of stress cycles, day after day, forcing the crack deeper into the metal. The bridge was literally counting down to failure, one vehicle at a time. Stress corrosion cracking is insidious. It thrives in the presence of moisture and tensile stress, advancing through the metal grain structure invisibly. No inspector could see it. No maintenance crew could stop it. The fracture was advancing on its own timeline. By December 1967, the crack had eaten through nearly the entire cross-section of eyebar 330. The bridge was holding on by a thread of steel, literally, and no one knew. The countdown had reached 0. At 5 o'clock on December 15th, 1967, eyebar 330 finally gave up. The crack raced through the last intact steel in a fraction of a second, and the chain, suddenly holding nothing, separated. Which means the entire load, hundreds of tons of steel deck, roadway, and rush hour traffic, instantly transferred to the adjacent eyebars. They weren't designed for that. They snapped in sequence, link after link, racing outward from the failure point. So the bridge didn't sag slowly or crack gradually, it disintegrated. The entire 1,750-foot span twisted, buckled, and plunged into the Ohio River in under 2 minutes. 46 vehicles, 46 lives. No warning, no second chance. And that's the brutal arithmetic of zero redundancy. One crack, one eyebar, one failure point. When it broke, there was nothing left to hold. The entire structure was only as strong as its weakest link. And here's the terrifying truth. Metal fatigue doesn't care what it's holding up. The same invisible cracking that killed the Silver Bridge has torn open aircraft fuselages at 30,000 feet and split ship hulls in open ocean. Because metal remembers. Every takeoff cycle bends an aircraft wing. Every wave slams a cargo ship's hull. Every rush hour load stresses a bridge member. The material counts every single cycle, and the crack advances whether you're flying, sailing, or driving. Which means the lesson from the Ohio River isn't about bridges. It's about physics. Any structure under cyclical loading is on a clock. The only question is whether you find the crack before it finds you. So the National Transportation Safety Board launched the most exhaustive bridge forensic investigation in American history. Divers pulled twisted steel from the frigid river bottom. Every eyebar, every pin, every fragment, cataloguing wreckage like aircraft crash debris. Under electron microscopes, metallurgists found it, eyebar 330, fractured clean through. The fracture surface told the story, stress corrosion cracking radiating from a tiny defect, decades of fatigue striations visible like tree rings, marking every load cycle the bridge had endured. And here's the failure that haunts engineers to this day. The crack was on the inside of the eyebar eye, hidden from view, impossible to inspect without disassembly. The bridge had been doomed for years, and no inspection regime could have caught it. So Congress moved fast. Within 18 months, the Federal Aid Highway Act of 1968 mandated the first ever national bridge inspection program. Every highway bridge in America, on a 2-year cycle, using uniform standards. 46 deaths had just rewritten infrastructure law. But the real revolution was fracture-critical member protocols. Engineers now had to identify every single component whose failure would collapse the entire structure. And those members got special inspection, special design rules, and mandatory redundancy. The eyebar lesson codified. And that's the legacy written in the Ohio River. 46 lives brought a safety revolution. Every bridge inspection, every redundancy requirement, every fracture-critical analysis traces back to December 15th, 1967. The bridge that taught us metal never forgets. So the lesson carved into the Ohio River that December isn't about bridges, it's about the universal law of fatigue. Every structure under cyclical stress is counting down to failure, and invisible cracks don't announce themselves until catastrophe. And 19 years later, metal fatigue struck again, this time at 24,000 feet, when Aloha Airlines Flight 243 lost 18 feet of fuselage mid-flight. Same physics, same invisible enemy, different altitude. Next time we're going up. Quick note, this is for education only and is not financial advice. Always do your own research before investing.